Now starting the webinar.
All right, Lance, I think you can take it.
Yeah, looks like we're live here. Well, welcome everybody to the webinar on the architectural solar continuum. This is a webinar, so when you jump in here, you're going to be muted. Let's just jump through some of the housekeeping here before we get into actual content. I think most people survived the pandemic here, so if you haven't seen Zoom, I guess there's going to be two options here to getting in your audio, either through your computer or through your phone. I find the phone is the most reliable, but the audio through your computer is probably more convenient. In the end, if you have troubles, so you can skip to the next slide here, Chris. We do have backup here from NREL comms team. Lady Maya's here to help. If you have any trouble with audio or any other problems, click on the chat button and send a message to the host. If you have questions throughout the webinar, we encourage that you ask them. We're going to handle them all at the end of the webinar, but you can ask them through this Q&A. I will go through them at the end. We'll try to get through as many as we can. I think the rest of the panelists will agree. If we don't get to them, we can provide contact information and we can answer questions afterward as well. Let's go ahead, Chris. So this is a webinar hosted by NREL and in collaboration with the Architectural Solar Association. The Architectural Solar Association is really the driving force behind this content, behind this partnership. So the National Renewable Energy Lab, NREL is where I'm coming from. We are one of the 17 national labs owned by the Department of Energy in the United States. We are the only national lab fully dedicated towards the deployment and development of renewable energy. The Architectural Solar Association is a trade association that has largely common goals between NREL is trying to achieve by representing a growing industry with the common goal of transforming building facades and other architectural surfaces into generating assets. In short, we want to put PV everywhere. ASA achieves this through expanding awareness, act as a supply chain resource, and developing standards. So this work that you're going to see today is a small piece of what has been enabled by a Department of Energy grant. It is funding NREL and ASA to work together on developing content that will be deployed through webinars like this one, in addition to content you'll see at the end here, a little sneak peek on our database and future learning content, with the goal of really breaking down barriers. And so this is funded by two offices of the Department of Energy, both the Solar Energy Technologies Office and the Building Technologies Office. And so this is, I think, really representative of what we're trying to do is really build a bridge between buildings and building professionals and PV deployment. So that is really what we're trying to do in this key barriers, inhibiting widespread adoption of architectural solar. So we'll be increasing penetration of on-site renewables and really driving towards energy efficient buildings. And really just to promote architectural solar as a concept and as a common ground for folks in these different industries to work together. So all of this is not done in a vacuum. All the content you see has been vetted by what we call the technical advisory group, the TAG. And you see a lot of companies and partners on the bottom there. If you are out there and you're interested in partnering with us in developing content or helping us, address any kind of this thing or worries or any kind of things you're working with as a company that's interested in architectural solar, please reach out. We want to work with more people. We'd be happy to include you. So this is going to be driven, I'll be effectively the master of ceremonies here. My name is Lance Wheeler. I'm a PhD scientist at the National Renewable Energy Lab. I'm also the group manager of materials physics. A lot of my interests are into the materials that enable building integrated photovoltaics or the deployment of building integrated photovoltaics. And that's really where I came across Stan and Chris. Stan Pipkin is the CEO of Lighthouse Solar. So he's actually in the world actually making buildings that really address the ideals of architectural solar. And Chris Kling is doing the same thing as a principal at Solmotive. They're also both leaders at the Architectural Solar Association, Stan being the design director and Chris, the technical director. And you'll be hearing from myself, and then you'll be hearing from Stan and Chris as we go on through this webinar. So at the end of this thing, you may be here for AIA credit. You are able to get AIA credit by attending this course. We'll follow up with some kind of a quiz. You'll answer some questions, supply your AIA number, and you'll get a credit for attending this. But when you complete this course, you should be able to define architectural solar and explain why it's important, define the 6 application categories of architectural solar, learn how to utilize a solar area ratio, a concept we've been developing internally here and are going to share with the world today. Understand key considerations associated with each of the categories. So we'll go through a number of categories of this architectural solar continuum. and to identify a range of installation types and where they fit on that architectural solar continuum. So I'm going to start at that first bullet point and just ask Stan, what is architectural solar to you?
Well, thanks, Lance, and welcome everybody. Appreciate the opportunity. This is really a central question we wanted to talk about today and why we think it's important and how we can start to use this as architects, designers, building professionals, and solar industry professionals. As you see in the slide that just came up, this is solar by any means, we'll say. And the reality is, you can apply any pejorative to this installation. It's unfortunately quite common, and it's what we think is, a very narrow solution where solar is solving a something that has very little relevance to a broader context. And so, if you look in the next slide, this is what we call building integrated photovoltaics, BIPV. It's on the other end of the spectrum, and it can be virtually invisible. It's fully integrated into any number of assemblies in a building. But in our analysis, we found that it also comes with some preconceived notions that it's too expensive, it's difficult to specify, and generally it's just somehow not ready for mainstream. And despite really the ambitious projections over the last 20 years, and even prior to that, BIPV is just not caught on in a way that we think it should. So the next slide gives you this is a very cursory historical, some context points, certainly not comprehensive, but what's really telling is that looking at solar in the context of architecture that has popped up in some key historical moments, and in places where you may not expect it. As early as the 40s, there was a competition set out by a glass manufacturer who was producing a insulated glass panel window, and it spurred architects all around the country to design houses that they were calling them solar houses. Not quite the technology we're looking at today, but it was architecture driven by a very specific program, and that took kind of keen acknowledgement of the building's relationship to the sun. So we'd call it passive solar, and it's ages old technology, but it was a moment in time when there was a popular recognition that this was a unique marriage. In the 70s, kind of this is around the energy crisis, one of the early impulses as solar technology, the active energy side of it, was getting off the ground. Architectural integration emerged just as the technology was coming into kind of a commercial application. So it signals to us that there is an impulse, it may be latent, but it's real, that architecture and solar go together in interesting ways. And if in the next slide, this is just a metric to say that in the intervening times between the 70s and today, one thing that's been really addressed aggressively by our industry is solar is a competitive energy source. So it's been commercialized. We're at grid parity in many parts of the world, and the cost issue is something that we've solved. So this next series of slides is just a quick smattering to say what's happening out there in various corners of the world are interesting applications of solar technologies in its various forms on various buildings. The reality is, we ask the question, why isn't this happening more often? And so that leads us to our work is to define architectural solar in a manner that empowers the industry to embrace this as a real design opportunity. We define it simply as solar energy generating technologies that have architectural significance or are coordinated with the architectural design process. And that has a couple key rationale that we think it's worth pointing out, just to keep in mind kind of through the balance of the presentation today. It's more than just aiming for one end of the spectrum or another, but it's looking at some of the kind of key considerations that solar can have when it's coordinated with the ethos and the practice of designing a building. Why architectural solar? Just in short, it's happening, and it's gaining scale. So it's not abstract. This is not a dream. It's places where you don't expect it, but it's real. What's quite interesting is, the way where the energies, call it the grid 2.0, or the modernization of the grid, is looking for energy sources close to the load. And honestly, most of the load currently in the US is at buildings. And so solar, an active energy system on a building, is as close to the load as possible, and it generates a lot of efficiencies at the grid level. It avoids transmission losses, which is a flip side of that application. When you put solar on a building, some places work better than others, and there's definitely affordances by west-facing or vertical applications, as opposed to just thinking of the roof only. The other dimension is this is being driven by some municipalities, which are putting out in the world very aggressive goals, which force the issue to look more creatively at where solar resources can be deployed. And finally, and this is sort of where we think it's most interesting for architects and designers, it can be a compelling and achievable design opportunity. So in the next slide, we ask a slightly more clarifying question is why do we develop a continuum? And we'll spend the rest of the conversation today on this topic, but the continuum is just to say that there are multiple places and applications that architectural solar can be expressed and can be developed. We think there's 3 key areas why looking at this from the lens of a continuum is important. One, we really think of it as a set of strategies. So these are not just canned solutions, but these are ways of looking at a building through the lens of energy and developing keen strategies. The other, from a process improvement, we found just in our work, and I think in the market, building owners are interested in exploring solar, but if it comes at the wrong time, it can actually be a liability and create hurdles, obstacles, and just general gridlock in the process of designing a building. Or if it's a retrofit, it could just be misapplied. So integrating it within the process yields results that really can be realized by all stakeholders. And finally, just to key on, this can be a real driver for innovation. And it's not just a design, not just a compelling aspect of a building, but it can really set in motion innovation that is across the entire building and or site in terms of its relation to energy generating capacity. So quickly, we'll go into this. This is a bit of an introduction for what Chris will take over in a minute. This is how we are codifying the continuum. And it's just to break down different applications in convenient groups that are excuse me, sorry about that. These are tool sets for a designer to start to imagine how to direct their efforts when applying solar into the context of a building project. So the key thing here is that as you move from left to right, the integration becomes more complex, and the requirement for architectural coordination also increases. So it is a sliding scale, and it's something to be mindful of as you move sort of across or up the continuum. And finally, the last slide here I'll just touch on is in a good example. Chris, if you want to forward it on to, the next slide here is located in NREL. This is where Lance is. NREL just happens to be an incredible example of a site that is utilizing actually all of the categories of solar deployment in one campus. And it speaks to their kind of rigor in exploring all the different ways that solar can be applied across both an open field and then built into the buildings in very strategic ways. And these are all essentially test labs. So they're looking at it both from a performative level, how the systems are performing, and also how the occupants of the site and the buildings are interacting with these technologies. So when we ask, can it be done? Yes, it can. And it's a good example where it's happening in one site in very interesting ways. I'll hand this off to Chris now, who's going to pepper you with a little bit of a brain teaser. So if you haven't fallen asleep, it's time to wake up now.
Hello, everyone. My name is Chris Klinga, and I serve as the Technical Director of ASA. And I'd like to take the time to ask you all a question that will help us gauge how you all perceive solar energy as it relates to architecture. And that question is, what is the most advantageous massing and building orientation for yearly solar kilowatt hour production, assuming that the building is a net zero building in the mid latitudes of the Northern Hemisphere, square or rectangular massing with a flat roof, and all surfaces having solar potential with no shading, and assuming the same floor area for all. So option A is a long building with a broad area facing south. Option B is that same building turned 90 degrees with that broad area facing east and west. And then option C is just a square version. And so the question here is, which one of these is best for solar production, or are they all equal? And my colleague, Lady Maya at NREL, will be taking over and facilitating the poll for everyone here. It's probably already popped up on your screen. So if you can answer, I will do so on my end as well. And I am not going to reveal the answer just yet. Or maybe Lady Maya will, but regardless, we'll move on, and we'll see where that answer takes us. It will be really interesting to see what everyone comes back with.
You
Lady
ready for me
Maya,
to share the results?
yeah, I think we can show the results. It'd be great if you could. So yeah, 52% stated a rectangular building that maximizes its southern exposure and minimizes its east-west exposure. And 10% said the correct answer, which is a rectangular building that maximizes its east-west exposure and minimizes its southern exposure. And then about the same said a square building, and then 29% said all are equal. So that tells me that my hunch is that there's more solar industry participation on this call than architectural. So that's really interesting. The correct answer is B, and folks wouldn't think that because that southern exposure is minimized. But at the end of the day, you have just more area on the east and west, whereas you're not putting solar on the north in option A. So you just have more solar area because that east and west is doubled and larger. So if that concept's still tough to get your head wrapped around, that's understandable. But hopefully as we progress here, we'll shed a little bit more light on it. So to jump into the continuum, the architectural solar continuum includes 6 top-level categories: site-applied photovoltaics, site-integrated photovoltaics, building-applied photovoltaics, externally integrated BIPV, which is building integrated photovoltaics, cladding integrated BIPV, and envelope integrated BIPV. As solar becomes more integrated and complex, the multifunctional benefits increase. As solar components share more cost with building components, the incremental installation cost goes down. One of the most interesting and counterintuitive concepts is energy density. On the left side of the spectrum, you have site-applied photovoltaics that are optimally oriented but require a fenced-off plot of land. On the right side of the spectrum, you have BIPV that may be suboptimally oriented, but shares a lot of space. Despite BIPV's efficiency shortfalls, it holds significant value that should never be overlooked from an energy density perspective. This concept may seem counterintuitive, but as we progress through the images of the continuum, we will review several examples that articulate the concept of how energy density changes with levels of integration. After we review each of the steps along the continuum, you'll be more prepared to make decisions that empower you to innovate and fully leverage integrated solutions to optimize project outcomes. So let's get into it. Site-applied photovoltaics is the least integrated solar application category in the architectural solar continuum. While site-applied photovoltaics has a low level of integration, it is considered architectural solar, assuming it is coordinated with the architectural design process. Site-applied PV can be broken up into 4 main categories. They include fixed tilt arrays, floating solar, single-axis trackers, and dual-axis trackers. The benefit of fixed tilt arrays being that they generally require less land, but yield less energy on a per kilowatt basis when compared to the trackers. Floating solar is great because it does utilize space that is otherwise underutilized in some instances. Site-integrated PV is our first foray into the definition of what we're calling integrated rather than applied. In contrast to applied technologies that don't have value beyond their energy production, we view the world of integrated as providing a multifunctional benefit. Site-integrated PV presents an opportunity to reduce complexity and increase energy generating potential by decoupling solar from a building. Site-integrated PV applications include solar accessories and furniture, such as solar-powered charging stations or outdoor lighting applications. These solutions can utilize PV to charge batteries that bring power to locations that may be more costly to retrofit. Parking canopies are the most common example of site canopies at work. Covered parking is a premium, and adding a solar carport to a project can have a substantial impact on the site's net energy use. Architectural structures and art installations present an opportunity to showcase an organization's commitment to renewable energy while adding aesthetic appeal to urban landscapes. And walking surfaces can integrate PV technology, utilizing vast surface areas that receive large amounts of light. Agrivoltaics offers an opportunity to co-locate solar and agricultural production, which can increase land use, reduce water consumption, and increase crop yield for certain species. Transit shelters are an essential part of public transportation infrastructure, and photovoltaics integrated into them not only provide shade and protection for commuters, but also generate electricity off-grid to power lighting, digital displays, and other amenities. Building applied photovoltaic systems are more integrated than site-based installations on the architectural solar continuum, mainly because they're on buildings themselves. That being said, being applied systems, they're installed externally to the building envelope and serve no additional function beyond energy production. Building applied PV typically consists of a flush-mounted single tilt or dual tilt system. Dual tilt systems broaden the solar curve and increase the kilowatt-hour potential of a roof. One of the major downsides of these systems is that they can take up roof space, and that roof space may be valuable for architectural programming. Externally integrated solar solutions are the least integrated BIPV solution on the architectural solar continuum. They are a PV that are integrated within exterior elements of a building and usually provide protection from weather, sunlight, or form a visual or physical barrier. These solutions sit at a high value point within the continuum because they are somewhat decoupled from the envelope, which reduces their complexity relative to more integrated BIPV, yet they still have clear multifunctional benefits. Specific applications for externally integrated PV could be a building awning that expands a building's footprint, sunshades installed as part of a building's facade that can block sunlight directly from entering windows or glazed areas during the summer months, but allow the low-angle winter sun to heat the space. Visual barriers such as mechanical screen walls offer an excellent opportunity to integrate solar within a barrier. Mechanical screen walls will visually conceal and dampen noise from mechanical equipment on a roof. Long span structures that span 2 adjacent building areas or shade the entire roof of a building present great opportunity to increase the site's energy generating potential. Double skin facades consist of an outer layer and an inner layer of glazing, creating an air gap or cavity between them. They offer an opportunity to retrofit aging architecture, as well as being easier to coordinate with the envelope itself. Physical barriers or glass railings are a great way to leverage the benefits of solar as safety glazing. Cladding integrated PV is 1 degree closer to the envelope integration by being components of a roof or a wall assembly. Typically, this is in the form of an outer weather barrier. Roof integrated cladding offers the best energy production opportunities, while wall systems can provide increased energy generation when expanding beyond the rooftop is required. Cladding is generally integrated either on a sloped roof, a wall, or a flat roof deck in the case of a walking surface. Roof integrated cladding offers the best energy production opportunities, while wall systems can provide increased energy generation when expanding beyond the rooftop. Solar roof tiles come in a wide range of shapes and sizes. The images shown here are the Tesla solar shingles in the lower left. And as they get larger and integrate with existing dissimilar roofs, they are less of a solar roof tile and become more of a PV module roof system. As in the upper image, the latter representing a means of integrating traditional solar modules as a roofing element itself. PV integrated wall cladding is now being offered by various manufacturers with various surface treatments that reduce solar production, with the benefit of customizing aesthetics and concealing the solar technology from view. Integrated solar floors, similar products can be integrated into a rooftop deck or balcony with the same methodologies utilized for pedestal-mounted pavers or deck tiles. In such an application, textured glass is typically utilized to form a non-slip surface. The envelope integrated category consists of solar technologies that form a physical barrier between conditioned and unconditioned, the unconditioned environment of the building. Vision glazing applications offer the best opportunity to apply solar technologies to large glass areas. Currently, there are several technologies being developed that are focused on this expansive market opportunity. Some utilize organic PV coatings that are nearly invisible, such as the images seen here. Others place solar cells within the perimeter of the window and direct light via film within the outboard laminate. And the most readily available option being amorphous silicon products that integrate thin film into an outbound laminate. Slope glazing offers the highest energy generating potential of the category and presents an opportunity to filter light in innovative ways. Crystalline technologies can be utilized similar to a frit pattern on glass, and thin film technologies can tune the visible light transmittance of glass by altering the thickness of their coating. Generally speaking, the more opaque a coating, the higher the efficiency. And high efficiency technology brings me to the spandrel glazing opportunities, which offers the best opportunity to integrate high efficiency technology. And this is because they're typically opaque. High efficiency opaque technologies are great for spandrel opportunities. So you might ask, that's all great, but how do I get started with my next project? And that's where we believe the best first step is to establish your energy goals and then assess what we call the solar area ratio. The solar area ratio, or SAR, is a preliminary tool to evaluate massing strategies and the feasibility of achieving energy offset goals with solar. At an early stage, you can identify the areas in which you can dedicate to solar, and the SAR can be used as a feedback tool while optimizing a design. At a low SAR, it will be very difficult to achieve aggressive offset goals. We encourage you to analyze your past projects to determine how your solar offsets have related to the solar area ratio. And simply put, the solar area ratio is the area you dedicate to solar as it compares to the conditioned floor area of the space. So you simply add up your floor area as you would in an EUI calculation, and you place the solar area that you would dedicate to solar over that. And that is a gross solar area. So in the case of the roof, it's the entire roof area. Or in the case, if you're going to install solar across an entire wall, it's wherever you would dedicate an area to solar. And so so I asked you all to look at your own projects and analyze them and really try to figure out what your solar area ratios have been on past projects. But until then, let's take a look at how solar area ratio relates to energy use intensity of a building. At later stages within the analysis and the design of a building, the building's EUI and solar performance can be used to determine the solar area ratio required to achieve net zero. You can then compare a solar area ratio that you can achieve to the net zero solar area ratio to understand your offset potential. You can also back into solar performance in terms of kBTU by dividing the building's EUI by the solar area ratio. This all is likely a bit over everyone's head today, but that's why we've developed a ton of educational material to support these concepts. And so as a next step, let's just take a look at a couple quick metrics to help this concept sink in. I know it's probably pretty dense from a technical perspective. So here, if we were to look at the mean US energy use intensity for several building types in the US, we would get this list. And we can go to Energy Star's portfolio manager to populate it. And it gives us the energy use intensity of all of these different building types in kBTU per square foot per year, the definition of EUI. And at the top, we have inputted the typical specific yield of 4 major steps in the architectural solar continuum. Note these values are location specific, so take these figures with a grain of salt. Our logic is that on the left side, site applied photovoltaics is at 1,500 kilowatt hours per kilowatt per year. And that's on the high end, and it should be achievable in a typical SAPV application within the US. SIPV is typically lower slope and sometimes suboptimally oriented. So we use 1,200 as a conservative figure. And then on the BAPV side of things, we assumed a 10-degree tilt facing south, which typically yields around 1,300 kilowatt hours per kilowatt in the middle of the country. And then vertical BIPV applications may see values closer to 900 kilowatt hours per kilowatt. And so when we use those and we compare and we combine them with the power density of the technologies, and for SAPV, based on the area that of a ground-mounted solar array, we could achieve 10 watts per square foot. SIPV can achieve much higher than that because we really just analyze it based on the area of the array itself. So 20 watts per square foot is achievable. And BAPV, typically it's around 10 for a rooftop system that's including the entire space that the solar is mounted to on a roof, including all the perimeter zones. And then on the BIPV side of things, 10 is also a good number. When we get to the site's potential in terms of kilowatt hours per square foot per year, we then get to the site's potential in terms of kilowatt hours per square foot per year by converting those figures into kBTU to make it apples to apples with EUI. And lastly, by dividing the building's EUI by the EUI of the PV, we can determine the net zero SAR for each of the applications. And in this example, in the office, you can see that a 52.9 EUI for the average US office, we would need 1.03 times as much area for a SAPV array as we would have floor area. And in the case of a site integrated PV array, like a carport, we would only need 65% of the floor area to accomplish our net energy goals. And then on the BAPV side of things, we would need 1.19% more area than our conditioned floor area. Anytime you see a value greater than 1, you would need to look beyond the rooftop to achieve net zero. And that's because as you add floors or or the roof is roughly the same area as the conditioned floor area for a one-story building. And it's always less for any building taller than 1 story. And in the case of BIPV, we would need to add 1.72 times. So by combining BIPV and BAPV, we can achieve net zero. But this is a tool that gives you a sense of how much area you'd need to get there. And so just to give you one last little take home on the path to net zero, if significant offset is a goal, it's critical for designers to consider the full continuum of integration opportunities. This is why we developed the architectural solar continuum. So architects and engineers don't just pigeonhole themselves into one subset of the continuum, but understand that it's all at their disposal. If you want to achieve net zero, think about maximizing floor-to-floor heights. By maximizing floor-to-floor heights, you're increasing the value of the wall as it relates to the floor area, which maximizes the solar area available. Optimizing building massing for the solar area ratio and orientation is going to increase your yields and increase your overall offset. And an SAR of greater than 1 means that rooftop alone cannot sustain the building. One needs to look beyond the rooftop to find a path to net zero. And so in the end, the net zero SAR is the EUI from the grid, or the building consumption EUI, divided by the EUI of the PV. And at this point, we'll open it up to questions. And Lance, feel free to throw any that you have that have popped up.
Yeah, let's start with the first question I got was actually on passive air heating using solar and its interface with PV even. I was just wondering how much experience you, Chris, or Stan have on doing air heating with solar, or any kind of interaction with that type of technology with PV.
I don't have any direct experience. I mean, I've heard of it being done, but yeah, it's been definitely a fringe concept over the years.
Stan,
Yeah, not specifically with passive air heating, but I think, when you look at sort of hybrid systems, there definitely is some solar and like active solar PV systems coupled with solar water heating that do some of the same kind of heat management. There's heat distribution that you can pull heat off of the panels to make them work more efficiently and then distribute that heat throughout the building, whether it's hydronic heating or just water heating or whatnot. So I think those are definitely technical solutions to kind of an aspect of what we're talking about, looking for the right set of marriages in a house. And those often depend on I would say they operate in very specific areas of the building, just given the complexity of some of those hybrid systems. But I personally don't have any experience with active air heating. I know there are strategies like trom walls and just ways to manipulate heat transfer in a building envelope that are analogous. But yeah, no direct experience with that. That's a good question.
I'm getting the correction here. It's active solar heating, not passive. So my mistake there. I do want to point out too that, my email address is certainly available on the web. I'm not sure if we have these posted on a slide here, but I definitely encourage people to reach out and continue conversations after this. And if there's something that you don't get an answer that you like, we can definitely continue the conversation later. I'll continue with a few other things. I got a question about opportunities for funding for BIPV or architectural solar. And so I did list a few of those in the chat. I guess, can everybody see that? The answers that I provide? So I have a few opportunities there. There have been explicit calls from, say, the Solar Energy Technologies Office looking for BIPV projects. I listed a few that are active right now. They're not specific to BIPV, but they could definitely be, they're not averse to it. Things like building projects or any kind of solar energy technologies funded research that can go in there. We had a question on the impact, and I guess I did have a short answer for Aaron in the chat here, but Chris and Stan, the question was on the trade-off between now you just put a highly absorbing material on your facade or roof that's going to impact your HVAC load. Can you just discuss the trade-offs in that, because you're now introducing a larger building heating or cooling load?
Well, I mean, I think in premise, if you're actually enclosing the envelope, then there would be an air gap, and you would have some level of insulation between the solar technology and the envelope. So that I don't have the data to understand whether or not you would increase the solar heat gain of those surfaces or not. In the instance of vision glazing, you would be placing opaque material, and you would reduce the solar heat gain theoretically by absorbing more light. In the case of spandrel opaque applications, I think a lot of research needs to be done on whether or not you're heating the envelope up in a way that is detrimental to the building. But yeah, maybe you can speak to that a little bit, Lance.
The one thing I was going to add is that I think that is a pretty open area in two different directions. I think intuitively it is going to increase your heating load, but is it significant? I think the answer is no there. I don't think it's significant. But you're also putting your PV into a thermal environment it's not used to. And so now you're pushing the limits of, what can this PV survive when it's not usually designed to be deployed this way? If you're thinking about, modules that are made for open racking and that sort of thing, where they have cooling on both sides.
Exactly.
So
I think that's the bigger question.
Yeah, these are open areas where I think there is research needed, and there was questions about, how do you get research funds to do this sort of thing? Yeah, these are questions I think needs to be answered better, and if you guys are interested in teaming up on something like that, I'd be happy to entertain that sort of thing. And I'm sure Chris and Stan would be as well. Stan, do you have thoughts on this?
Yeah, I think it's I reflect back on the question that was posed, kind of the brain teaser. It's not intuitive from how we imagine, like, what solar harvest, where the best solar harvest is. And we generally think that it's the south, but if, the inverse of this question is where is the highest heat gain? And it really is east and west. If you have a building that has, predominant exposure to the east and west, because you get more normal or perpendicular exposure to the sun. And so that's kind of the reason why the production of the east and west from a solar perspective is actually higher, because you get more direct sunlight. And so it sets up, a contradictory kind of set of design challenges where your heat gain could be maximized or could be increased, but as well as your solar potential yield. And so I think for us, that's the right problem to solve. So, it really is taking the active solar portion of it at a level that's tantamount to building design. And so I don't think it's an easy solution. Like, it is very site dependent and spurs kind of creative solutions. One of the systems we looked at is just a set of louvers that's for shade management on the side of a building. And so it actually increases the surface area of a facade, but in a very interesting way to help manage heat gain to an otherwise fully glazed facade. So I think I don't think it's a simple answer, and I think it's actually the point of departure for really interesting design solutions. So yeah, I think it's a great question.
I'll jump in here and just add that George Kelly did add a good comment of just at least a good way to think about this right away is that if you put a dark absorbing PV on the side of your building, that PV is 22 to 23% efficient at best at this point. And so any of that absorbed energy, 23% of that is actually not going to be contributed towards heat load. That's going to be electricity. But there are, within the visible wavelengths, if it's black, that's 50% of the sun's energy. So the rest of those infrared wavelengths, those could also be contributed towards heat gain. And it's really how the rest of that panel is designed. And so you can design, like infrared reflecting coatings, things like low emissivity coatings on your panels to prevent some of this added load that might come along with putting black things on the side of your building. But it's all kind of pointing towards it is not, it is a fairly new space for folks. And I think you will be heating your building out more than you usually would, but it is a significant, and there's ways around it, I think, too, as ways to sort of prevent it. I see Chris has something to jump in there with.
Yeah, I mean, I think the other thing to keep in mind is that today there are spandrel areas that are opaque, and there's shadow boxes that increase the heat gain of buildings. And I think the real question is if you add solar to those same assemblies, would it increase the heat gain in a big way? And my general take is that at least it's, being reduced by what we're converting to electricity. So when you compare one to another, I think it's a negligible amount of heat gain when there are already opaque frit patterns that are doing exactly this.
There's a comment by Dieter. I apologize if I'm saying your wrong name, but I'll share with everybody. It's a link to the International Energy Association or agency on BIPV. And so some of the things people are digging into is addressed by some of this international work. And I think it kind of just brings up a comment I wanted to bring up is in the US, there is definitely less architectural solar going on than there is in, say, the EU. They have more, I would say, resources, or I guess we're playing a little bit of catch up here on some of the things we're working on. Chris, so one of the questions I had in here while I'm copying that to everybody is on urban heat island effects, and actually it all connects towards this idea of what happens when you start to absorb a lot of energy into your buildings on the facade. Have you given that any thought?
I mean, I think it would, yeah, I mean, I think at the end of the day, we are going to be absorbing more energy, which is a good thing for the grid. But, in terms of how it, yeah, and for, as long as that energy is going to the grid, it's better than, getting absorbed by concrete. I don't know what I think about that beyond that, but maybe I'm missing the point of the question.
That's there, Stan.
Yeah, I mean, I think short of looking specifically at, how a building surface would perform in comparison to the alternative, if it was not considered an active energy surface, I think typically, you think of Greece, like all surfaces are painted white. It's highly reflective in some towns, some small villages. I think that is a strategy, and kind of there's been an effort to paint roofs white. TPO and other membranes have moved in that direction, have higher albedo in certain areas. But when you start to look at just the vertical surfaces of buildings, I think there are real considerations about, what are the limits of albedo, let's say, and then what are the trade-offs for just, a building that is some form of mass in sunlight. So I would tend to agree that if there's a marginal benefit to pull some of that energy into electricity and then power other functions of the building, it's a marginal, it's a benefit. I think there's, again, I would go back to this level of kind of inquiry at a building level. It starts to look like an ecosystemic discussion of how we're looking at, urban development codes and practices. So it's not just one building, but it's the entire fabric that's built. And so these questions need to be surfaced in order to push the conversation further beyond just a single building. And that's kind of what one of our premises is that, a more careful kind of investigation at a building level inherently invokes, a larger site level discussion. And it starts to develop sort of development practices that are well beyond the purview of just a single developer or a single architect, but it's the kind of generalized conversation that needs to happen as well. So again, apologies for not having a simple answer to the question, but I think it's the right approach to inquiry.
I've got an easy one to answer, and that was, will the slides be shared and the contact information be shared? I'm happy to share my contact information in the chat here.
Absolutely.
And I'm not sure about the slides, but the recording of the presentation we posted to both the NREL YouTube page as well as the ASA YouTube page. This would be another question here. I guess, Chris, the other thing we could do is post some of the other activities we'll be doing. As a
Yeah,
back.
well, we have that. Once we want to conclude here, we've got a final slide on that. But given that we've got 9 minutes left,
I do have, yeah, sorry, Chris, a couple questions popping up now.
yeah, go for it.
From Anonymous, it says, as you pointed out, PV windows at their high level of integration can offset lower watts per square foot that comes with the technology, but use more building surface. How do you foresee the building integration can be driven in the construction? Sorry, another question popped up while I was reading it. The building integration can be driven by the construction industry as glazers typically do not see wire electrical connections or components. So some of the integration difficulties with PV windows in general.
Yeah, I mean, I think generally speaking, BIPV requires a coordinated effort in a big way. And so the architect needs to be involved. The general contractor needs to pull together the right trades that are all that all understand their duties and their scope of works. So typically what we see is that, glazers will integrate the technologies into their glazing systems, but then there's an engineering firm that coordinates the design and how all of the glazing units get wired together. And electrician, if a glazer deals with wiring, it's usually only on the DC side if they have to deal with it at all, because maybe the wiring is integrated into the glazing units themselves. And then from the glazing units to the aggregation of the glazing units through the strings, sometimes that happens. Usually that's happening with the building electrician that's coordinated with, and then the inverters and the point of interconnection are usually dealt with by the building electrician, and ideally they're familiar with solar. And if they're not, then we'll see solar contractors pulled in to help facilitate that process.
I would just add, Lance, this question I think gets at a really interesting development. We've tried participating in an effort to reclassify solar glazing as an energy efficiency measure rather than a typical interconnected system. It's not to say it's going to happen overnight, but it's when you look at kind of the relative yield that a glazed wall could have towards a building's consumption, there's an argument to make that the output of those windows inverted could be fed directly into branch circuits in the building and bypass the traditional interconnection, which in a lot of cases is a disproportionate expense and difficult measure to coordinate well on certain building types. So again, it's asking the question and pushing that can lead to innovation that would have otherwise not been uncovered. It's an effort we're pursuing. It's something certainly still requires quite a bit of agreement from the regulatory agencies, but it's a very interesting outcome from just simply asking these questions in a certain way. And just there is something called balcony solar. Sounds like a little bit of a gimmick, but it's at some level it's similar to this idea that solar can be placed very strategically in small amounts and be essentially plugged into the branch circuits of a building. So, which is a radically different approach to integrating solar.
I can follow up really quick on what Stan said, maybe pivot to the next question here is this idea of PV windows and thinking about them as more of a efficiency metric rather than, or a, building efficiency rather than, photons in versus electrons out, how much energy yield you have. I think it makes a lot of sense that the innovation in Windows has stagnated quite a bit from, double pane windows with low E coatings. It's been the same out there for many decades. So people think about vacuum insulated glazing, they think about triple glazing. they've really struggled to take off. PV glazing makes a lot of sense. You can start looking at even just small gains in generation. They can offset what you might lose by having a more energy efficient or thermally efficient system. So I think PV windows do make a lot of sense in that case. And just to pivot into another question, which was, has anybody conducted techno-economic analysis of BIPV applications? I'll definitely let Chris and Stan take this one as well. But from a window or a glass perspective, where glass is a cladding material, the current state of PV is that glass, and this is true for thin film and for silicon, glass is the most expensive and most carbon intensive piece of that panel. So if you're thinking about saving money and saving carbon, if you can dual use your glass by making it both photovoltaic and a piece of your facade, it makes a lot of sense just intuitively. But I know Chris has crunched some numbers on techno-economics of these sort of things. And I think Nova was looking at, or was asking specifically about LCOE. And so I don't know if we have numbers like that. But yeah, you have to incorporate a lot of things like installation costs and offsets from other materials you'd be offsetting when you're putting into the building, which does make that LCOE calculation a lot more difficult than it is for, say, utility scale solar. Chris, do you have any examples on that or at least thoughts to add?
Yeah, I mean, I think that our upcoming case study on Boulder Commons this is actually a good segue, kind of our upcoming events. We will be, presenting a techno-economic analysis of the Boulder Commons project based on the readily available, the prior studies that have been done by RMI on that project. So they have some techno-economic analysis done on the cladding systems that were used at Boulder Commons, and we'll be taking their findings and putting them through our lens and presenting those on December. It says Tuesday, December 3rd. Yeah, I guess it's December 3rd. I had the 1st in my head, but it's the first Tuesday of December coming up in a couple months. So I encourage you all to, join in there. And then we will also publish a paper that's associated with that webinar. And then following up in March of 2025, early March, on March 4th, we're going to have a database webinar. So in parallel to all of this work, we've been developing a database of projects. We have around 260 projects currently in our database that is going from an Excel format to migrating into the cloud on the openei.org platform. So that's a wiki-based database that's funded by the Department of Energy, and we are building out an architectural solar project database. And we will be unveiling that database in March. And the idea is that it will provide a view into techno-economic analysis on projects in due time, assuming that the information is available for those projects. If it's not, then the information will be focused on energy production of the projects and how the solar, the offset potential of the solar. Beyond that, we have additional case studies planned for the idea is that our case studies will encompass the full architectural solar continuum. So this first case study is really focused on cladding integrated in BAPV. And then we will do a future case study on site integrated PV, and as well as one on envelope integrated. And I also encourage you all to take our free short course on heatspring.org. It's about an hour in length and good for 2 AIA credits, as well as NAPCEP, 1 NAPCEP credit. This webinar as well is good for AIA credit, assuming you complete the follow-up survey. So if you provided your AIA number previously in the registration process, you will be getting a survey for a quiz to get AIA credit.
And Chris and Lance, I think it's a good question, and just to maybe put a challenge back out to the audience. When we do LCOE evaluations of every solar project, whether it's architectural solar, fully integrated, or just a type of retrofit. So it's part of our industry has substantiated our presence. Like the question from the public is, why would you do it unless it has an attractive return? And I think the interesting thing about architectural solar is it does put some of the onus back on developers and architects to say, what is the value of a particular architectural program? And when we start to evaluate how PV is integrated into an assembly and you're pulling it apart and trying to understand what the LCOE of that energy equation is, we really have to look carefully at, what value are we putting on the architectural program? Because in some cases, the fact that solar has a return for that system puts the program, the architectural program, cultural, social, how the building's occupied, how it performs for its occupants in a very different light. And I think that's a language that clearly developers understand from a real estate perspective, but a lot of architects, it remains kind of squishy. And I think we're asking the architects to engage, that conversation more comprehensively. So it is, yes, something that has to be looked at on each project at a specific level, though, I'd say.
Well, I think we're at 3 o'clock here, 3 o'clock Mountain Time. I think it's best to wrap up. I think there are other questions rolling into the chat. We can either stick around and answer those, or we can move those to email. What do you think is best here, Chris?
I'm happy to keep chatting and talking about it if folks, for a little bit. And if there's
The direct question here is on fire protection, how it's handled in BIPV. I know you've thought about this a lot, Chris. For systems in the US. So in Europe, there's lots of more restrictions is what the questioner says. So how is fire protection handled? And then is there a national electrical code that applies to facade mounted BIPV? If so, please advise.
Yeah. So right now, there are rapid shutdown standards being developed in the US. Those standards have mainly been focused on rooftop solar and the ability for a fireman to interact with a solar system. And so in a rooftop applications, it makes a ton of sense from a rapid shutdown perspective, because you don't want firefighter interacting with solar panels on a roof where they may need to vent a roof. On a facade, it's a different question because firefighters don't necessarily regularly vent facades or interact facades in the same way. I think fire protection in facades, from my perspective, really needs to be more focused on what is the risk of the solar system arcing and causing a fire, rather than being safe to deal with by fire personnel. So in certain jurisdictions today, it's not totally clear in the US whether or not rapid shutdown devices are required for facade mounted applications. There's plenty of places in the code to point to those being focused on roof mounted applications or overhead applications. But yeah, it's an unknown today, but I think that the real research needs to be done on like whether or not the assemblies have risk of accelerating a fire in a facade. And that's where a lot of fire testing needs to happen.
Stan, anything to add there?
No, I think that covers it.
All right, I think we've covered everything in the chat. We will follow up with that survey. With the survey for the AIA credit, and make sure you guys have our contact information if you'd like to reach out and continue these conversations. But in general, I just appreciate everybody being here, and thank you very much.
Yeah, thanks
Thanks
everyone.
for all the great questions. Appreciate your participation.
It was a pleasure.